works, but let us see what can we do. So let me start with the problem, okay? So you have, for example, you have an uphill here. Let me just model it with a right angle triangle. So that is the ground level, and then you have a little bit of uphill, and then you shoot a ball or something with some. So this angle, let me first of all give you this angle. This is the inclination angle of this inclined plane, surface, and then I shoot a ball or whatever with given speed v naught, but of course I should say given velocity, because I want to show it with a vector. So its magnitude is v naught, and its direction makes an angle beta different, might be not exactly the same. So in my picture it's probably this is the same, but no. Alpha is fixed, beta I fix it, and I shoot my ball or my particle, and it takes a trajectory and actually hits this inclined plane at some point. Yes? I want to calculate this length. Okay? So I want to see how long, how far it goes on this uphill. So let me call it D. I mean, if I call this one O, if I call this one A, I want to calculate this. So what I provided for you is, of course, there are some instruments that you can really measure this incline. So I think it's very, very simple one these days. And of course, you can fix in a way that you really shoot it with angle beta regarding to this inclined plane. And then you can probably know about the speed that you can shoot. So these are the things I give you, alpha, beta, v naught are all given. And I want to see that if I ignore the air drag, of course, where this will end up on this inclined plane. So my goal is to calculate this distance d. And then when I say that calculate this distance d, it means that give me a formula so that expresses d in terms of the given parameters of the problem, including alpha, beta, and v naught. Yes? And that is the point. Okay, as I told you, because I don't know your physics background, let us just start thinking about the problem together. So how do you think about the problem? So if you want to start solving this problem, what do you do? Now, I mean, what is the general setup if you want to solve this mechanical problem, yes? So, where do you start? Yes?
Splitting up the vector in x and y, on the x and y axis.
No, before that, completely from scratch. Because you know that this is not mathematics, this is a law of nature, yes? But that law of nature is expressed in a mathematical form. What is that law of nature? It's a very, very elegant and simple formula discovered by, yes? So let me tell you something. In mathematics, we have some axioms, yes? So it means that we accept them to be true, and then we start deducing true statements from that one. The axioms in physics, axioms, so in mathematics, axioms are just axioms. For example, consider the chess game. So one axiom is that the bishop moves, I don't know, in a crossway. That is not, we can say why, yes? That's just the rule we accept and we enjoy the game. So mathematical structure is very similar to the chess game or whatever game it is. So you have a set of rules, you accept them, and then you make a structure on top of that. That's a mathematical structure. The first principles, you don't need to prove anything. You accept them. And then, of course, you want to keep the number of them as low as possible. It's always, yeah, that's no problem. Yeah. Yes, and then in mathematics we essentially can have any statement. But in physics we cannot say any statement. We can have axioms again and say that if the nature works like that, these are the consequences. But there is a big if really the nature works like that or not, it comes from experiment. That's the only point. So you do some experiments, you get motivated, okay, this seems to be the rule governing this phenomena. Yes, and then you state it as an axiom. You say that, okay, if the world works like that, this is my axiom, then I will actually calculate things. And then what happens is that if you go in the future, might be you get some deviations from the predictions of that law. And it means what it means, then you do two things. First, you start recalculating things. Might be you have done some errors in your calculations that you see the deviation. Or if you are now completely sure that you haven't done any mistakes in your calculations, then it means that the law itself should be modified in a way that it should actually contain these consequences that you are looking at. So this is the way that physics works. Okay, but now here you have this phenomenon, and then you want to understand it. So there's one law governing this. If the person who invented that or discovered that is true. What was that law? What's the law? All mechanical problems are starting from which law? Actually, three laws.
Okay, so Newton's law.
Newton's laws, yes. So the second one is actually very important. So the second law, so the first law actually tells you that there exists an inertial reference frame. What does it mean? It means that there is a frame of reference in which if the total force is zero, the acceleration is zero. Okay, so that's an axiom because we cannot prove that such an inertial frame actually exists. We accept that there is one, and then we work on in it. And in it's Newton's second law. Here we don't need the third law. Here, but what is the Newton's second law? So it's a very, very simple and elegant formula, yes?
F equals m.
F equals to ma, but now I don't know how you have studied that, but we know that F is a vector. So let me just denote it with a vector. M, the mass of my particle, is just a scalar, but acceleration is also a vector. Force is a vector because it not only contains magnitude, but also direction. The same is true for acceleration, yes? And then, so this is the total force. If you want, I can write this here. So this is the vector sum of all forces acting on my particle, yes? And then this is the acceleration. And of course, what is the acceleration? If I have, so acceleration is the derivative of velocity over time. This means the derivative with respect to time. So that's the Leibniz notation. Usually in physics, people use the Leibniz notation more. Okay, and then of course, velocity itself is the derivative of position with respect to time. So this is dr. R is the vector pointing, so that locates the position of my particle, yes, and then dt, and then I have another d dt here, okay? So this d dt is the one that I have written here. It means the derivative with respect to time, and v itself is the derivative of position with respect to time. So then it means that this becomes the second derivative of position with respect to time. And this fancy way is just the second derivative. You can write it like that. Yes? But in physics, usually they use it. And then in physics, it's also very common. Instead of putting primes, they put dots. So they say R double dot. So this means dot is derivative with respect to time. If it is with respect to other variable, because time is very important parameter in physics, so they have invented. So if you want to say, you can say that the velocity is R dot, the first derivative of position, and then you can say that acceleration is V dot, which is equal to R double dot. Yeah, these are the notations used in physics books, but it just derivative, yes? Okay, so we have to start from here, because that is the only law governing this phenomenon. Yes, so what I have to do, I have to understand the total force acting on my particle. I have excluded the air drag, so I don't need to be worried about any friction force. So there's only one force acting in this game, and what that is. So if you shoot the particle, of course in the beginning you shoot it, but when it is in the way, you don't have any effect on it. So there's only one force acting on this, and that's the force of gravity, yes? And the force of gravity close to the Earth can be approximated with this one, yes? So the total force here is what? The force of gravity, which is the mass, yes? But multiplied by vector g, yes? G is the acceleration due to gravity, but because that's an acceleration, it has to be a vector again. Yes, usually G is the magnitude, without this symbol, is the magnitude of that vector, if you want to. And this is an experimental fact that it would be around 9.8 meters per second squared, yes? But we don't need to be worried about that, we just take it as G. So whenever I use G, I mean the magnitude of the vector of the acceleration due to gravity. So it's always positive in my notation. So G is just a positive number which represents the magnitude of that force. Okay, so the total force in this case is this, and that is this. So I put them equal to each other, yes? So this means that MA is equal to mg. And then I cancel this m. By the way, what type of product is this? It's like a number multiplied by a vector. So it would be a vector parallel to A. Yes? And so I can cancel m from both sides, and then A becomes G. Yes? Okay. But now I am working in only 2 dimensions, so I can safely work with 2 coordinates, not the third one. Yes? So let us just ignore the third dimension for examples. But can you just tell me now, if I want to start this, what I have to do, I have to, usually, you see there are no coordinate systems. In physics, when I am doing some experiments, there are not coordinate systems in nature. But if I want to work and solve something mathematically, I myself set up a coordinate system. And that coordinate system is completely arbitrary. Yes, you really don't need to care about that. But of course, if you are careless, you will set up the coordinate system in a way that the mathematical equations become complicated. So this is important to choose the best possible, that comes by experience by the best choice for the coordinate system. What is probably the natural coordinate system that you have seen in projectile motions is probably taking the horizontal to be the ground level and the other one vertical to that. So I will set up a coordinate system. Whenever I start, you see that is the formula in physics, but if I want to do some mathematics, I have to set up a coordinate system, and the coordinate system is completely arbitrary. Of course, different coordinate systems will give rise to complexity, more complex mathematical equations. So let us take this one and work here. If I do that, it means that, what can I write for A? A is the set, so what can I write for R? So let me call this one the position of my particle here. I can denote it by this vector R. Yes? So this position has an x, so what is the components of this vector? Let me call this one x, let me call this one y. If someone asks you what are x and y, I would say that x and y are components of this vector, and this vector is called the position vector. It denotes the position of my particle. So if I say that what is r, you remember in analytic form, a vector is here 2 components because I'm working in 2 dimensions. The projection of the vector on the x-axis, I called it myself x, and the projection of this vector onto the y-axis, I myself called it y. Yes? Is that right? Okay, and it turns out that if I want to find the derivative, I need to calculate the second derivative. Let us do it a little bit as you are familiar with. So I just take the second derivative of r, but it turns out we haven't talked about this in our course, but if you want to take the derivative of a vector, you can do it component-wise. Yes? So this is the only thing that I am actually selling you without proof. So I take the derivative of x, and I take the derivative of y. Yes? Okay, now this is the vector A. Okay, but can you tell me how can I write vector G? Where is G? If I want to show somehow vector G, what is the direction of vector G?
Straight down.
It's straight down, yes? So this would be, for example, here, straight down, and this is vector G. But be careful, this vector G is position independent. Even if the particle is here, the acceleration is exactly the same, even if the particle here. So if you are around the Earth, this acceleration is always pointing downward, yes? So that is why you remember when we were talking about vectors, we say that the vectors doesn't have any locations. So the vector is just a vector independent of the location of that vector. But now can you tell me what are the components? You need to tell me what is the x component. Do you remember what was the notion of the component? You need to project it onto the x and y axis and then look at the shadows, yes? And then that size, that length, considering the direction, is the components of your vector. So what is the length? If I project this vector onto the x-axis, what is that length?
0.
0. Yeah, so the x component of my vector is 0. Yes? What is the y component? I have to project it onto the y. So what is that? Here we have it, yes? So because the length of this vector is a number, yes? But I told you that for that number I use letter G. And I told you that by my convention I will take it positive. So what can I write there? 0 and?
9.8.
Forget about 9.8, I want to put G, but not G. Because I have put the coordinate system pointing upwards. So that should be minus G. I could have chosen the y direction in that case, then I had to write positive G, yes? So here I have to write negative G. So don't get confused. This is my vector. This is a number, yes? So that is it. And then I equate these two vectors coming from the Newton's second law, yes? So what happens is this. I have x double dot, y double dot, sorry, so x double prime, y double prime is equal to 0 and minus G. Yes? As simple as, so you see that I started from Newton's second law. I want you to see the connection. If Newton's second law was not there, we couldn't write this. And then we learned that this is a vector is supposed to be equal to another vector. Vectors are equal if and only if the components are equal correspondingly. So what happens, it means that I get a system that x double dot is 0 and then y double dot is negative G. Yes? But remember, what is x and y? I want you to don't get confused. In mathematics, I write y equals to f of x. It means y is a function of x. This is the standard symbols that we use, the relations. But here, can I say x and y are functions? And if yes, function of what?
They're a function of the path.
No, not in this form.
Okay.
Not function of the path. Yes?
Is the function of the acceleration?
No? No, simpler than that. They are function of? So let us say it in this way. What is the initial x and y coordinates? when my particle starts moving. What is the x and what is y?